Hi, in this video I'm going to show how to detect objects using a region-based convolutional neural network, which is generated based on a pre-trained convolutional neural network, in this case a ResNet. In the previous video that is in the descriptions of this video, I used a convolutional network made from the scratch, but in here it's going to be a pre-trained, which is more convenient and also more powerful. As also mentioned in the other video, the MATLAB Deep Learning Toolbox have three main ways of detecting objects. One of them is detecting the object without telling you where the object is. The other one, very common, is segmentation, in which all the pixels are classified into a particular object category, for example, car, pavement, pedestrian, building, etc. But in this case, we're using region-based object detection, in which the object is detected and the bounding box surrounding the object is provided as well. It's kind of a classification problem and also a regression problem as well. Okay, so let's do this video. We're basically doing a walkthrough through this example, which is also in the reference. You have to click Open Live Script to go to the example. Okay, that'll take us to here. And you have to execute these commands or you can just basically download this file into here, which is basically the training data, and then you're just gonna load the data for training. You have to unzip this file and then load the data. Okay, so let's just do it. And we have just a field, so let's just take the field out. So we have the raw data, which is a table, and the table has the images and the corresponding bounding boxes. So notice that we have the category in the column title, so when we train, that's going to be automatically inferred, the category, and the bounding box is going to determine where the vehicle is. And for most of the time, we have only one bounding box. We have 4 elements, which is the minimum x, minimum y, maximum x, maximum y. And sometimes we have 2 of them because we found 2 cars, but most of the time it's only 1 car. Okay, so now let's partition the data. We have a total of 295 entries. So we're gonna get the height. The height of the table is basically a number of samples, 295. And let's do a random shuffling. First, let's reset the seed. And now let's get the shuffle indexes, which are basically 295 sample indexes shuffle around. It's good to shuffle around the data. It's better for training because if you have ordered data, the order in which you provide the data can give some bias into a network and can mess it up. So it's always good to shuffle it most of the times, I guess. Okay, so we're gonna take 60% of the samples for training. So that's gonna end on index 177. So we're gonna pick up the first 77 indexes from the shuffle index, and this is going to be used to access the data, and that's going to give us the segment of the table with 177 training inputs with the vehicle and bounding boxes. And then we're going to go on into 178 until 10% of the shuffle indexes. So we're going to take 60% for training, 10% for validation. So that's going to be about 30 indexes. We do the same. We take the shuffle indexes and we use the indexes to access those shuffle indexes and get the validation table, which is going to contain 30 entries. And then we just pick up the remainder, which is about 80 something, and do the same to get the final 88 samples for testing. So training is for training the weights of the convolutional region-based network. The validation is applied during each epoch to assess how precise it is without the bias of the training data, so we can easily tell if we are overfitting or not. and the final testing of the network, of the train network, is done on this. Okay, so now let's wrap those table data into data stores. Okay, so first in the table we only have images, so we need the image data store to load those paths of the images files into data, into in-memory image data, and that's what this one is gonna do. Okay, let's run it. Yeah, so basically they have the list of files and it's gonna load them. And the bounding box label data store is for the bounding box for the vehicle. So we're gonna just pass the vehicle column, and this will pass the image column. Okay, so the problem of detecting an object with a bounding box like this is so common that the computer vision toolbox of MATLAB has this data store in particular for that. Okay, so we're gonna do the same for the validation data and the test data. And then we have to combine the images and bounding boxes with a combined data store. It's gonna look like this. You can see the image and the bounding box data stores. So let's do also the same for validation and testing. Okay, so let's take a sample from the training data. We're just gonna read one element. We have the image and the category and the bounding box, two bounding box actually. So there are two cars with two categories because there are two cars. So let's take the first and second column, and we use the insert shape. This is a computer vision toolbox command to put the bounding box within the image so that we can see it. And then we resize it. We basically we duplicate the size of the image. Is 224 by 336. It's gonna be like 400 something, 600 something after doing this. And you can see it now. Yeah, well, 400 by 600. Yeah, and now we're gonna take a look at it. Yeah, effectively you can see that there were two bounding boxes and two categories for each one of them. Okay, so that's the training data. Okay, now let's create the region-based convolutional network, and for that we have to specify the input size, which is going to be 224 by 224. This is different from the size of the training data, so it has to be pre-processed for resizing, and for that we have this transform. Okay, so we need to apply the pre-processing. And that we're gonna use first. We need to create the anchors. The anchor boxes is basically the sizes that you expect the boxes to be. For example, we expect boxes maybe being like this or a little bit bigger. We don't expect a box that be the size of this one. We don't expect a box to be the size of this one or something like that. We have like some estimates, and we're gonna have 3 estimates for this. And using the data, the anchor boxes are gonna be determined by this function again from the MATLAB Deep Learning Toolbox. So this is gonna give us the bounding boxes. Okay, so it's gonna go through pre-processed data, which is gonna take as input the image, the bounding box, and the category. Okay, so it needs to figure out. We know that our image size is gonna be 224 by 224, so we had to figure out the scale. So it uses this formula for that, and we figure out, okay, the first the first dimension is fine, so it's 1, and the second one has to decrease by 33%. Okay, so basically we are gonna rescale the image, and now we have the output image size as we expect. But also we have to update the bounding box, and for that, for the image we use IM resize. This is from the image processing toolbox. And also we use VBox resize, and this is from the computer vision toolbox. Okay, so both of them have to be resized the same way, and we did it. Okay, so we're done with pre-processing, and we will use that function again later. Okay, so now we have the anchor boxes, and you can see the 3 of them. We wanted 3, we got 3. and one is small, another is kind of medium, and the other one is the larger one. Okay, now we want to have the pre-trained convolutional neural network, which is a ResNet 50, and we're gonna take a quick look at it. Okay, here's our ResNet, and basically it's called ResNet because it's a residual net. We have a residual, it means that we take an upstream layer and feed the output to a downstream layer. So we can see that we have a convolution, a normalization, ReLU, the usual transforms. I think the convolution is tried, if I'm not mistaken. Yeah, no, it's not. No, it's not the stripe. It must be coming from some other part. But anyway, okay. So this branch is almost empty, and this pattern is going to be followed a lot of times, and eventually you have finally the classification output with 1000. So this network is trained to detect 1000 objects. It is a well-trained network with the fully connected layer, etc. Okay. So now we are going to use the fasterRCNNLayers to create the region-based convolutional network for detecting objects in bounding boxes. And for that, we need to specify the anchor boxes that we just got. We need to specify the input size, which we already got, and the number of classes, which is 1. We find out that in here, because we have table data, and in the table we have only one column for vehicles. We have to subtract one because the image column is not counted. But for example, if we have something like pedestrians, stop signs, then they will come in 2 more columns. So that's why we're getting the width of the table to determine the number of classes, and in this case it's only 1. Okay, so we provide the anchor box, number of classes, input size, and the pre-trained network. And also we need to specify from which layer we're gonna start doing the region-based layers. And in this case, we select number 40. 40 is this one. So it's not the last one, it's not the one of the earliest one. So how do you select which layer you're gonna insert your region-based layers? That the example mentioned that it has to be done through empirical analysis. Okay, so now we have everything. So now let's create our graph, and we're gonna take a quick look at it. Okay, here's the network, and you can see that it is exactly the same up to the layer that we chose. And in here you're gonna see all the inserted layers, and at the end we have the classification of 4, which is the minimum xy, maximum xy. This is the bounding box. It's like a regression problem. Okay, so and also we have the classification in here, which is basically to detect the object. Okay, so now we have the graph, but this graph is not trained for the particular object detection of the car. This ResNet that we provide here was trained for something else. So we want to train to detect cars. Okay, so now that's what we're gonna do. First, we have to do some data augmentation. The data augmentation is very important because it can expand our training set, because we apply affine transformations like rotation, translation, scaling. We can insert noise. We can do vertical flipping, horizontal flipping, and a lot of transformation that can extend basically our data, multiply our data, but also makes the training robust to those type of conditions that could happen in real life. Okay, so for that we provide this callback in here that is going to apply a affine transformation. In this case is a reflection, a simple horizontal reflection. Okay, so let's create the data store, and the method is still not executed, but we're going to sample it. We're going to sample it 4 times. We're going to call read to get the data, and from the data we get the image, the bounding box, and we're going to use insert reshape to put the bounding box in the image, and we're going to collect it into the 4 images. And finally, we're going to put it into a montage to display it. And then we reset again so that the training goes fine. Okay, I'm not going to debug through this. I'm just going to run it, but it's going to hit the breakpoint of this augmented data method. Okay, so in here we have the data, which is basically the image, bounding box, and category. We're going to apply the transform, and it's basically an horizontal reflection, and you can see here which is a diagonal with -1 to flip the X. Okay, and then we get the affine output view from the size of the image, and from the transform is basically the limits, and we provide both of them to the IMWarp method. This is basically image processing toolbox stuff. There's plenty of documentation on it, and we're gonna pass the view, we're gonna pass the transform, and then we're gonna do a fine transformation in the image, and the same that we do in the image we have to do with the bounding box as well in here, which is this. And for that we use the VBox warp. This is from the image processing toolbox, and this is from computer vision toolbox. Okay, so we apply exactly the same in both of them, and that's going to be our output data, and that's what is going to happen during training, because the data store is going to call this method. It's going to call this method a read whenever we supply training data to a network for training. Okay, so we can see here that the only transformation is basically horizontal flipping, and the bounding boxes, you can see that they got adapted to have the right position. Okay. Okay, now let's get the data for training. Now we have the augmented data. We have to preprocess it. We can also see in here that the data is 224 by 336. We have to adapt it to be 224 by 224, and for that we have the preprocessed data callback. So we need to apply another transform into the data store that takes the augmented data store as the input. For validation, we don't do the augmentation. For the validation data, we don't do augmentation, so we just pass it directly with the preprocessing. Okay. And now we're gonna read the training data to see how the preprocessing looks. We just do the same, insert shape, resize, basically multiply the size by 2. Basically the aspect ratio of the image changed. Okay, for training we're gonna use stochastic gradient descent with momentum, 10 epochs, mini batch, small 1, 2. We specify checkpoint to save the state of the training, in case like we lost electricity or something, a machine crashes or something like that. They can allow us to continue the training because it can take a long time. And in the training option, we supply the validation data. This is the validation data store that we already created. That is to test for overfitting. Okay. Okay, for some reason it's not taking it. Okay, finally it took it. Okay. And now we're going to use the trainFasterRCNNObjectDetector method, which is going to take the training data. This is our data store. We can see in here we have the L graph, which is the recurrent, the region-based convolutional neural network that we create based on the ResNet, but also has the output of the bounding boxes. We have the options that we create in here. And this parameter is important. It basically says that if the object detected is below 30% of the anchor boxes, is detected as a negative. If it is above 60% up to 100%, then it's detected as a positive. So the output of this is going to be a train detector. So let's run it. It's going to take a while. Whoops. Let's see. let's take a look at how much GPU this is using. I'm gonna stop it and then use the pre-trained network in here because it takes a lot of time. We can see that initially has a 56% accuracy and it's using 7% of the GPU, which is pretty fine, pretty good. Okay, it arrived to iteration number 50 and the accuracy increased dramatically to 98%. Okay, still using a bunch of 7% of GPU, so that's good. But still, we're gonna break here because that takes a lot of time. So we're just gonna load the pre-trained one, get the detector, and now we're gonna use the test data. We're just gonna use the first one just to sample it. We're gonna resize it to the expected size of the network, and then we're gonna use the detect method. So the detector return from the training is gonna have a method detect that takes as an input the image, and it's gonna give us the bounding box and the corresponding confidence. So we have a couple of vehicles. We have the two bounding boxes for them. The first one is 91% confidence and the second one is 52%. Okay, so now let's insert those bounding boxes and the scores using this computer vision toolbox function into the image. Let's insert them and show the image to see the result. Okay, so this is gonna be a different image, different from the original one, and we can see that the real car was detected with 91% confidence, while the false car was detected with 52% confidence, so it's pretty low confidence, so we could have ignored it. Okay, now let's evaluate the performance. So let's create a transform for the test data store to pre-process the data to make it fit to the 224 by 224 by 3 size. Okay, so we're gonna pass that data store into the detect method, so it's gonna be smart enough to run the detector on all the test data, and let's get the results. This doesn't take long, but I'm gonna pass anyway. Okay, so we have the results. Let's take a look at the results, which are nothing more than the bounding boxes. Sometimes the images do not have a car at all, so they're empty. Sometimes they have one car. They say the confidence was 100% a vehicle, and sometimes they found a couple of cars. I think they never find 3 cars in a picture. Okay, so now let's evaluate this with the evaluate detection precision. This is a function again from the computer vision toolbox, and it's smart enough to be able to compare this table data against a data store. There are different objects, but still they convey the same information. The image, the bounding box, and the label is able to get that information and compare both of them. So let's take a look at the result of this. And the average precision is going to be 75%, which could be improved if we have more data. And then let's take a look at the recall and precision. Okay, so this can be seen as the following. The precision is basically the probability of is inclines toward the probability of not having false positives, and the other one is the recall is for not is inclining towards the probability of false negatives. So you can see this as the following. When you have a low recall, it means that I don't care about there's gonna be a lot of false negatives. So for example, could be a lot of cars around that I don't detect them as cars. That is fine. Those are false negatives. I accept that. But if I say that there's a car, there's gonna be 100%, as you can see here, 100% probability that it is a car. So if the network says it is a car, it's really a car. But you're gonna miss a lot of cars. That's a problem of being down here. That's the conservative approach, and the extreme liberal approach is saying, okay, I'm not gonna fail no negative. I'm not gonna have no negative false negatives. So if there's a car, most likely I'm gonna find it. So in here we don't got a low false negatives, but we got a lot of false positives. So with 85%, so there's a chance that we say, okay, that is a car, but it's not really a car. So probably the right balance is somewhere around here, in which we have, okay, false positive 91%, and yeah, we don't have so many false negatives. Okay, so to recap, we created a region-based convolutional network based on a pre-trained convolutional network, which was the ResNet 50, and we trained that region-based network with some data with bounding boxes and cars. And the advantage of this approach is that it's faster because the convolutional network was pre-trained, and it's also more powerful. So it's kind of convenient. We just have to supply some data to adapt an existing network to the problem that we're trying to solve, which is in this case detecting cars on the streets. Okay, thank you very much for watching.